Every single time you buy a coffee, book a flight, or move money around, there's this invisible bodyguard for your data working behind the scenes. Its job is to make sure our digital world doesn't just completely fall apart. That bodyguard is the SQL transaction, and today we're going to pull back the curtain and see exactly how it works. So let's get right into it. To really get why this is so critical, let's start with a simple scenario. Picture this. You're at an ATM. You pop your card in, you punch in your PIN. What could possibly go wrong, right? Well, as it turns out, a whole lot. You might be surprised. All right, let's set the stage for a little disaster. Meet Homer and Marge. They have a joint bank account, and on one fateful day, they both decide they need some cash. So they head to two different ATMs at the exact same moment. Now watch this closely, because this is where everything goes sideways. Their account starts with $400. First, Homer's ATM checks the balance. It sees $400. Okay, but at almost the exact same millisecond, Marge's ATM also checks the balance. And what does it see? You guessed it, $400. Now Homer withdraws $100, so his machine calculates the new balance should be $300. Marge withdraws $50, and her machine calculates the new balance should be $350. And here comes the chaos. Homer's transaction saves first, setting the balance to $300. For a split second, all is well. But then, Marge's transaction saves, and since her ATM has absolutely no idea what Homer just did, it just overwrites his change, setting the final balance to $350? Wait, what? The correct balance should be $250, right? 400 minus 100 minus 50. The bank just literally gave away free money. This nightmare scenario is called a race condition, and it's a textbook example of data corruption. So, how on earth do we stop this kind of financial anarchy? Well, the solution, the hero of our story, is a concept called a transaction. The best way to think of it is as a sacred, unbreakable contract. It's a way of bundling a whole sequence of operations together and telling the database, listen, either all of these steps happen successfully or none of them do. There is no in-between. And to make sure this contract is absolutely ironclad, every transaction has to pass something called the ACID test. And no, we're not talking about chemistry here. ACID is a super powerful acronym for 4 promises the database makes to keep your data safe. First up, we've got A for atomic. This is the all-or-nothing promise. In our ATM story, the entire withdrawal, checking the balance, spitting out the cash, updating the new balance, is treated as one single, indivisible action, one atomic unit. If any part of that fails, the whole thing gets erased. No half-finished business, period. C stands for consistency. This is all about making sure the database's own internal rules are never broken. For example, if there's a rule that an account balance can't go below 0, any transaction that tries to do that will just fail. The database guarantees that it only ever moves from one valid state to another valid state. I is for isolation, and folks, this is the magic bullet that solves our ATM problem. Isolation guarantees that even if thousands of transactions are running at the same time, each one acts as if it's the only thing happening in the entire world. It's like putting Homer's and Marge's withdrawals in 2 separate, completely soundproofed rooms so they can't interfere with each other. And finally, D for durability. This is the promise that once a transaction is successfully completed or committed, its changes are permanent. They're written in stone. The power could go out, the server could crash a millisecond later, it doesn't matter. That data is safe and will be there when the system comes back online. So because of these promises, every single transaction has one of 2 possible destinies. It either succeeds and is made permanent, or it fails and is completely wiped away, as if it never even happened. The 2 commands that control this destiny are commit and rollback. Commit is the finish line. You're telling the database, everything went perfectly, save my changes forever. Rollback, on the other hand, is the giant red emergency eject button. It screams, something went wrong, undo everything I just did, and let's pretend this never happened. Okay, now this is where things get really, really interesting. That I for isolation, the perfect soundproof room, it sounds amazing, right? But perfect safety always comes at a cost. And in this case, that cost is performance. You see, the strongest, most perfect form of isolation, the one that gives you total safety, can really slow things down. It basically forces transactions to get into a single file line and wait their turn, and that can create huge bottlenecks. So, what do databases do? They offer a compromise. They give us developers different isolation levels to choose from.
Think of it like a sliding scale between perfect safety and maximum speed. At the very top, you have serializable. That's our perfect soundproof room. But as you go down the list, you start to relax the rules to get more performance. And when you relax those rules, you start to open the door for some very strange behaviors. What some people call ghosts in the machine.
When you weaken isolation, you risk running into what are known as data anomalies. Now, these aren't bugs in the database. They are the predictable and sometimes pretty terrifying consequences of choosing speed over absolute safety. Let's take a look at a few of these ghosts. First up is the dirty read. Imagine transaction 1 makes a change, but it hasn't committed it yet. Transaction 2 comes along and reads that temporary, dirty data. But then, plot twist, transaction 1 fails and rolls back. So now, transaction 2 is operating based on data that technically never existed. Kind of spooky. Next, we've got the non-repeatable read. In this case, your transaction reads some data, let's say an average score. Then, before your transaction is done, another transaction swoops in, changes that data, and commits its change. When your transaction goes to read that same average score again, the value has changed. The read isn't repeatable, and that can cause all sorts of chaos in your logic. And maybe the most ghostly of them all is the phantom read. This is when you run the same exact query twice in one transaction, but the second time, new rows have just mysteriously appeared or disappeared. This happens because another transaction inserted or deleted records that happen to match your query. It's like trying to count things in a room while ghosts are walking in and out. So, how do these different levels protect you? This table lays it all out. At the very bottom, read uncommitted is the Wild West. All 3 anomalies can happen. You move up to read committed, and you're now safe from dirty reads. Go up again to repeatable read, and you've blocked non-repeatable reads too. But it's only when you get to the very top, to serializable, that you're finally protected from everything.
And here's something that's really important to know for the real world. A super popular database like Postgres, its default setting is read committed. Just think about that for a second. That means, out of the box, your app is vulnerable to non-repeatable reads and phantom reads, unless you explicitly know to go in there and change that setting. This brings us to the final, crucial point, what some people call the developer's dilemma. Knowing all of this, how do you actually write code that's both safe and reliable, without grinding your application to a halt? Okay, let's boil it all down. First, always group related operations, like a bank withdrawal, into a single transaction. Second, you have to remember that any isolation level weaker than serializable is a calculated risk. You should only use those weaker levels if you've proven there's a performance problem and you understand exactly which ghosts you might be letting in the door. And finally, here's a pro tip. If your transaction only reads data, you can set it to read only. This can make even the weaker, faster levels much safer. And that really brings us to the final question I want to leave you with in this constant battle between performance and correctness, between speed and safety. How much risk are you willing to take? The answer is going to be different for every application, but now you have the tools to make that decision wisely. Thanks for watching.